Welcome back to our series on probability theory. I'm Mark Ledbetter. I'm going to go over the solutions for the fourth out-of-class exercise set assigned. And again, these numbers are corresponding to the ninth edition of the book by Hogg, Tennis, and Zimmerman, Probability and Statistical Inference. So we're going to have 6 essay questions that have been assigned by a professor. Now, 3 of these are going to be selected for a test. The student only has time to study 3 questions. So we want to find out the probability that of the questions studied, at least one is selected for the test. Now, we're going to be selecting without replacement because it doesn't make sense for the same question to be assigned twice or 3 times, right? So capital N is equal to 6. And then the category of interest, the question studied, that's going to be N1. That's going to be 3. The student has time to study 3. And of course, N2 is N minus N1, which is 6 minus 3, which is going to be 3. And 3 are going to be selected. That's N. So little n, 3. Okay, and so with this we have that x equals number of studied questions selected for the test. Okay, and so f of x is going to be n1, choose x, and then n2, choose n minus x, and then divided by n over little n, choose little n. And we want the probability that x is at least 1, which is equal to 1 minus the probability that x is less than 1. And the only value of x that x can take that is less than 1 is 0. So this is 1 minus the probability that x is equal to 0. And so we are going to fill in our values. So this is 1 minus, and so N1 is going to be 3, and x is going to be here 0, and then N2 is 3, and N minus x is going to be 3, and because it's 3 minus 0. And then we're going to have capital N, which is 6, choose little n, which is 3. And so we have 1 minus. Now 3 choose 0. Remember, this is 3 factorial over 0 factorial, 3 minus 0 factorial. So this is the same, and of course this is 1. So the whole thing is 1. Likewise, 3 choose 3. There's only one way we can do this. So this is 1 times 1. And then we have 6 choose 3. This is going to be 6 factorial over 3 factorial, 3 factorial. And so 6 factorial is 6 times 5, 4, 3, 2, 1. And then I have 3, 2, 1 for 3 factorial. And then I have 3 factorial again, which is 6. And so I'm going to have 20. And so this is going to be 1 minus 1 over 20, which is going to be 19 over 20. And that is our answer. So there is a 95% chance that at least one of the questions that were studied will be selected for the test. That's pretty good odds, except that only gets you a 33 and a third, right? So it's still not very good. Well, what's the probability that all 3 are selected? This is going to be the probability that x is equal to 3. And so we have n1, which is 3, and now x is 3. And now N2 is still 3, and this is going to be N minus x, so that's going to be 3 minus 3. And then we're going to have 6 choose 3. Okay. And so 3 choose 3 is 1, 3 choose 0 is 1, and we determine that 6 choose 3 is 20. So this is going to be 1 over 20. Not a very good, so only a 5% chance or a 0.05 probability. So not a very good probability there. Now, what's the probability that exactly 2 are selected? And so this is going to be the probability that x is equal to 2. N1, again, is 3. X is 2. N2 is 3. 3 minus 2 is 1. Over 6 choose 3. So the denominator stays the same. And now we have 3 choose 2, that's going to be 3. And 3 choose 1, that's going to be 3. And so we have 9 over 20, which is about a 0.45, or is a 0.45 probability. So a 45% chance that exactly 2 are selected. And again, that's not a very good grade if you don't know the other questions. All right. So now let's look at the next question. This is a question taken from section 2.5-7, problem number 7 for the 10th edition. And we have a Michigan Lotto 47. So the state selects 6 balls randomly from 47 numbered balls. These balls are numbered from 1 to 47, as you might imagine. The player selects 6 different numbers from the first 47 positive integers. And the prizes are given for matching all 6 numbers, that's the jackpot. 5 numbers, $2,500. 4 numbers, $100. 3 numbers, $5. Not very good for that. We want to find the probability of matching all 6 numbers. So again, all of this is selected without replacement. So capital N is going to be 47. N1 are the 6 balls that are selected by the state. N2 is the difference there. That actually, we're going to say that, So that's right. N2 is going to be 47 minus 6, which is 41. Now, little n equals 6. And we want x equal to 6. That's x equals the number of integers selected by player that match the numbers selected by the state. Okay. So we want to find the probability that x is equal to 6. All 6 numbers are matching. So this is going to be N1, choose x, which is 6. And then we've got 41, choose 0, because we don't want any of the balls that weren't, or the numbers that weren't selected by the player to be matched. Okay. And then we have capital N, which is 47, choose 6. Okay. Now 6 choose 6 is just 1. And 41 choose 0 is again just 1. And so we have to find 47 choose 6. And this is going to be 47 factorial divided by 6 factorial and divided by 41 factorial. And when we use, or we can use a key on the calculator or on the computer, and we're going to get 1 over 10,737,573. Okay. Now, if you want to do this longhand, we can do 47 times 46 times 45 times 44 times 43 times 42 times 41 factorial. Right? So, because this is going to be 41 times 40 times 39 times 2 times 1. So this is 41 factorial at the end of this. And then we have 41 factorial here, and so those can cancel out and become 1. And then we have 6 factorial, and 6 factorial is 720, but we'll leave this as 6 times 5 times 4 times 3 times 2 times 1. And if we look up here, we can see some values. 6 goes into 42 7 times. And 5 goes into 45 9 times. And then 4 goes into 44 11 times. And then 2 will go into let's see, so 2 will go into 46 23 times. Okay. And then we can do 9 is 3, and that is 1. And so you can reduce this quite significantly to 47 times 23 times 3 times 11 times 43 times 7. Okay, which will give you this 10,737,573. Very small probability here. In this problem, this is 2.4-6, we are going to suppose that approximately 75% of American youth have health insurance, and we're going to take a random sample of n equals 15 American youth. All right, so we're going to let x equal the number of youth in the sample that do have health insurance. And we want to know, how is x distributed? Well, we can assume using the 5% rule that n equals 15 is less than 5% of the population of American youth, right? Difficult word for me to say with the S on the end. So that means that they're independent by using this 5% rule. And if that's the case, then P is equal to 0.75, because we're saying X is the number that do have health insurance, and this says 75% do have health insurance. Okay, so P equals 0.75. There are two categories: health insurance, have health insurance, don't have health insurance. They're independent, and we know n is fixed. Therefore, x is a binomial distribution with n equals 15 and p equals 0.75. We want to find the probability that x is at least 10. So this is the probability that x is greater than or equal to 10. Now, we have p equals 0.75, and we can't find that on our binomial table here. Okay? So our binomial table, we see the p value goes up to 0.5. What we do see is a 0.25. So what we're going to do is we're going to look at this in a different way so that we can be clever and use this table even though the value of p is not listed. So let's think about this. We're saying that out of 15 youths, at least 10 have health insurance. That's 10, 11, 12, 13, 14, or 15. Now, what if y is the number of youth, American youth, that do not have health insurance? Well, in this case, x plus y has to equal 15. So there'd be 5 that did not have, 4, 3, 2, 1, or 0. Okay. So we want this. It's going to be, so this, the probability that x is greater than or equal to 10 can be rewritten. We have x plus y is 15. I want to solve for y. Y is going to equal 15 minus x. Now, I'm going to do a transformation from here to y. And I need 15 minus x on the left side. The first step is that I'm going to make x is negative here. I'm going to make x negative. So probability that negative x, now when I multiply both sides by a -1, okay, I have to flip the inequality. So that's the first step. And then I'm going to add 15 to both sides. So I have 15 minus x less than or equal to 15 minus 10. And this is the probability that y is less than or equal to 5, where y is a binomial with n equals 15, but p equals 0.25. Okay? So because x has a probability of 0.75, y is its complement, there has to be a probability of 0.25 that you don't have health insurance. So now I can just look at my table for 5. Let's see, n is 15, so I need to come down to n equals 15. And n equals 15 is here. And x, or y in this case, is going to be 5, and p is equal to 0.25. That's going to be 0.8516. All right, so we're being clever with this. Now, so that was at least 10. That was greater than or equal to 10. We want to find the probability that x is at most 10. So x is less than or equal to 10. And we're going to do the same transformation. So the next thing we do is the probability that negative x is greater than or equal to negative 10. And that's equal to the probability that 15 minus x is greater than or equal to 15 minus 10, which is equal to the probability that y is greater than or equal to 5. Remember, we can look up y in our binomial table because y has a probability of occurring of 0.25, which is listed in our table. But the table has cumulative distribution, the CDF, not greater than. So this, if y is greater than or equal to 5, this is going to equal 1 minus the probability that y is less than 5. Or I can rewrite this as 1 minus the probability that y is less than or equal to 4. So the reason that I change this is because the equal to sign, the cumulative, is what the table has. Don't forget to subtract this number from 1. So we have 1 minus. Now let's go look at our table for y equals 4. And so now y equals 4. Whoops. I need to get rid of this. I'm going to circle the 0.25 here. And so now it's 4. And so it's minus 0.6865. And that's going to be 0.3135. And that's our answer. Now we want to find the probability that x is equal to 10. This is going to be the probability that negative x is equal to negative 10, which is equal to the probability that 15 minus x is equal to 15 minus 10, which is the probability that y is equal to 5. And that's going to be the probability that y is less than or equal to 5 minus the probability that y is less than or equal to 4. Okay? And we can look both of these up in the table. In fact, we have these numbers up above. Here's the less than or equal to 5, so that's 0.8516. And then the 4 is 0.6865. And I'm going to use a calculator for this one to make sure I don't make a simple subtraction mistake. 0.8516 minus 0.6865 gives me 0.1651. Okay. Now, they're asking us for the standard deviation in the mean of x. So remember that x is a binomial 15.75. So mu is equal to n times p, which is 15 times 0.75, or 3/4. So 0.75 times 15 gives me 11.25. And the standard deviation, sigma, is equal to the square root of sigma squared, which is the square root of n times p times q, which is the square root of 15 times 0.75 times 0.25, which is the square root of 2.8125, which is about 1.67705, etc. So I'm going to say 1.6771. Now, actually, I'm going to do this to, I'm going to give 3 decimal places, but you could argue that we only need 1 since x is a whole number, right? Okay. Now, I added on a question that was not in the book, and I said, well, let y equal the number of American youth without health insurance in the sample. Find the probability that y is equal to 5. Well, remember that y is binomial 15.25, and this is the probability that y is equal to 5. Again, I didn't choose wisely because it's the same answer that we had for D that we already looked up. It's the probability that y is less than or equal to 5 minus the probability that y is less than or equal to 4, which from our table was 0.8516 minus 0.6865, which we had right up here, 8516 minus 0.6865, I believe, which was 0.1651. Okay. The next problem in this exercise set is 2.4-10. Now, it's important that we be very careful with reading this so that we understand what kind of problem this is. Now, of course, it's in section 2.4, so we know that this is going to be binomial. However, we should be able to identify this even without knowing which section it's in. So the mint, this mint, type of mint, has a label weight of 20.4 grams. And the manufacturer says that the probability that a mint weighs more than 20.7 grams is 0.9. So let x equals the number of mints, let x equal the number of mints that weigh more than 20.7, which is the same number here that they gave us the probability for, in a sample of 8. So n equals 8. And if we assume independence, then we have a binomial distribution because p equals 0.90 is the probability that any individual mint weighs more than 20.7 grams, and they're independent, so that means that this is constant probability. And we have n equals 8, and we have, so we know the number of trials, and we know that the category is either they weigh more than 20.7 grams or they don't. Or not. So 2 categories. And we have independence. It's a binomial. So x is a binomial distribution with 8 for n and 0.9 for p. we want to find the probability that x equals 8. We could do a transformation and use p equals 0.1 in the table, or we can just calculate it, which is probably the easiest thing to do. So this is n factorial over x factorial, n minus x factorial, p to the x, q to the n minus x. This is going to be, so n is 8 factorial over 8 factorial, 0 factorial, because 8 minus 8 is 0, and then p is 0.9 to the 8th, and then we have 0.1 to the 8 minus 8, which is 0, and that's going to be a 1. This is a 1, so we have 0.9 to the 8th, which is equal to 0.430467121, which is about 0.4305. Remember that we should go to 4 decimal places in this class for probability at least, unless otherwise specified. Now I want to know the probability that x is less than or equal to 6. I do not want to calculate 6 probabilities, so I am going to make the transformation. I'm going to say let y equal 8 minus x, because n is 8. So with this, the probability that x is less than or equal to 6 is the probability that negative x is greater than or equal to negative 6, which is equal to the probability that 8 minus x is greater than or equal to 8 minus 6. So now we have the probability that y is greater than or equal to 2, which is 1 minus the probability that y is less than 2, which is 1 minus the probability that y is less than or equal to 1, which is 1 minus, with p, y is binomial 8, and p is 0.1. So I want n equals 8, y, or x equals 1 for 0.1 p. Not on this n anymore. We're back at n equals 8. So we're going to come back to n equals 8, p equals 0.1, and y was 1, if I remember correctly, so 0.8131. Which is 0.1869. Okay. Now, the probability that x is at least, at least 6, which is 1 minus the probability that x is less than 6, which is 1 minus the probability that x is less than or equal to 5, which is 1 minus the probability that negative x is greater than or equal to negative 5, which is equal to 1 minus the probability that 8 minus x is greater than or equal to 8 minus 5, add 8 to both sides, which is equal to 1 minus the probability that y is greater than or equal to 3, which is 1 minus the probability, 1 minus 1 minus, this has to be less than, yes, okay, so 1 minus the probability y is less than 3, which is equal to probability that y is less than 3, which is the probability y is less than or equal to 2, which is equal to 0.9619. Okay, problem 2.5-1. We have an excellent free throw shooter who's going to attempt several free throws until she misses. So if her probability of making a free throw is 0.9, what's the probability of her having her first miss on the 13th attempt or later? Okay, so let x equal number of free throws required for first miss, not making. So the probability of making a free throw is 0.9. So we're interested, the probability of miss is going to be 0.1, so Q is going to be 0.9 in this case. And X is going to be greater than or equal to 13. So we want the probability that X is greater than or equal to 13. Now remember that the probability that X is greater than K, not greater than or equal to, is Q to the K. So this is going to be the probability that X is greater than 12, which means that this is going to be Q to the 12, which is 0.1 or 0.9, to the 12th. And so when we take 0.9, raise it to the 12th power, we get 0.2824, 29, etc. So to 4 decimal places, 0.2824. And that is our answer. Now let's assume that she's going to continue throwing until she has 3 misses. What's the probability that her third miss occurs on the 30th attempt? So this is the probability that X is equal to 30, where X is the number of attempts until the rth, in this case third, miss. Okay, so X is going to have a negative binomial distribution with P equals 0.1, because this is misses, not making shots, and R equals 3. And so f of X, or P of X equals little x, is equal to X minus 1, choose R minus 1, P to the R, Q to the X minus R. Okay? So what we're going to do here is we're going to plug in X is equal to 30. So probability X is equal to 30 is equal to 30 minus 1. R is 3 minus 1. P is 0.1 to the 3, which is R. Q is 0.9. 30 minus 3. So we end up with 29 choose 2 times 0.1 cubed times 0.9 to the 27th. So my calculator does do combinations, so 21 math and then choose 2 is going to equal 406 times 0.1 cubed times 0.9 to the 27th. So that will equal times 0.1 cubed times 0.9 to the 27th gives me 0.023687, etc., which to 4 decimal places is 0.0236. All right. So now let's move on to the next problem, and we're going to do 2-5-3. Now, we have a different basketball player that can make a free throw 60% of the time. Let X equal the minimum number of free throws that this player must attempt to make a total of 10 shots. Or just, not the minimum, the number of free throws that this player must attempt to make a total of 10 shots. Okay? We want to give the mean, the variance, and the standard deviation of x. Well, x is a negative binomial with p equal to 0.6 and r, let's see, so free throws to make a total of r is 10. Okay. So the mean, mu, is equal to r over p, which is 10 divided by 0.6, which could be rewritten as 100 over 6. And 100 divided by 6 is 16 2/3, or 6, so that would be an equals here, or approximately 16.67. Okay, that would be fine. And then sigma squared is going to equal, let's see, that's going to be RQ over P squared. So R is 10, Q is going to be 0.4, and 0.6 squared. So we have 4 over 0.36, which is also, let's see, 1 over 0.9, 10 over 0.9, that's right. So, which that's approximately 11.11. Okay? So it's 100 over 9, or 10 over 0.9. So now, sigma is going to be the square root of sigma squared, which is going to be the square root of 100 over 9, which is going to give me 10 over 3, which is 3 1/3, which is approximately 3.33. Okay. Now we want to find the probability that x is equal to 16. So this is going to be x minus 1, r minus 1, q, p, not q, p to the r, q to the x minus r, which is going to be 15 choose 9 times 0.6 to the r, which is 10, and 0.4 to the 16 minus 10, or 6. And so this is going to give us, let's see, 15 choose 9 is 5,005, then times 0.6 to the 10th, 0.4 to the 6th, times 0.6 to the 10th, times 0.4 to the 6th, and I get 0.123,958, which will be 1.1240 to 4 decimal places. Now we're going to move on to 2.6-2. So x has a Poisson distribution with a variance of 3. Find the probability that x is equal to 2. So lambda equals 3. Because remember, sigma squared equals mu and equals lambda. Mu is lambda and sigma squared is lambda for this distribution. And f of x is equal to lambda to the x, e to the negative lambda over x factorial. And so lambda is 3 to the x, e to the negative 3 over x factorial. So the probability that x is equal to 2 is f of 2, the PMF, which is 3 squared e to the negative 3 over 2 factorial, which is just 2. So this is 9 halves e to the negative 3. That's an exact answer. And so I have 9 times second e to the negative 3, close those parentheses, divided by 2 gives me 0.224041, etc., which is 0.2240. Now another way we could do this is use the Poisson table. And so, or probability x is equal to 2 is equal to the probability that x is less than or equal to 2 minus the probability that x is less than or equal to 1. To see this, the probability that x is less than or equal to 2 is the probability that x equals 0 plus the probability x equals 1 plus the probability x equals 2. That is there. And then we have minus, and then we have the probability that x is equal to 0 plus the probability that x is equal to 1. So we're getting rid of these. Because we have a subtraction here, we're getting rid of these, and so that leaves us the probability that x is equal to 2. So one way to see that. And this is when lambda is equal to 3, so Poisson, lambda is equal to 3. I'm going to have to come to here, and 2. So 2 and 1. So we're going to take these two numbers, 0.423 minus, am I doing this right? Am I looking at the right problem? Yeah, so x equals 2. So we've got 0.423 minus 0.199. 0.423 minus 0.199 gives me 0.224. So this is accurate to 4 decimal places in this particular case, so that's nice. All right, let's move on to 26-4. We're given that the probability that x is equal to 4, we want to find the probability that x is equal to 4 if x has a Poisson distribution such that 3 times the probability x is equal to 1 is equal to the probability that x is equal to 2. So this is 3 times, and so the probability x is equal to 1. So f of x here is lambda to the x e to the negative lambda over x factorial. So the probability x is equal to 1 is going to be lambda to the 1, e to the negative lambda over 1 factorial, and then this is going to equal lambda squared e to the negative lambda over 2 factorial. And so we have 3 lambda e to the negative lambda is equal to 1/2 lambda squared e to the negative lambda. Do not cancel out. You can both have e to the negative lambda. We can factor that out, which is fine. So, but we have a quadratic equation here, so this is true if and only if 1/2 lambda squared e to the negative lambda minus 3 lambda e to the negative lambda is equal to 0. So I've subtracted this from both sides. Okay? I wanted my square term in lambda to be the positive, have a positive coefficient. Now, what I can do is I can say 1/2 lambda squared minus 3 lambda times e to the negative lambda equals 0. Well, e to the negative lambda is never equal to 0. So this is true if and only if 1/2 lambda squared minus 3 lambda is equal to 0. If you try to cancel out lambdas, you're going to miss a possible solution. Don't do that. That would be wrong. So what we have is we can factor out a lambda out of both of these. So we have 1/2 lambda minus 3 times lambda equals 0. So this is true if 1/2 lambda minus 3 is equal to 0 or lambda is equal to 0. Well, lambda cannot be equal to 0. Lambda is always greater than 0. That is our requirement for lambda. So that implies that 1/2 lambda is equal to 3. So lambda is equal to 6. And therefore, f of x is equal to 6 to the x, e to the negative 6 over x factorial, and the probability x is equal to 4 equals f of 4 equals 6 to the 4th, e to the, oops, I know what lambda is here, that's 6. E to the negative 6 over 4 factorial. This is going to be 6 to the 4th is 1296 over 4 factorial is 24, which is 54, e to the negative 6. And this is approximately 0.13385, so 0.1339. The other way we could do this is the probability that x is equal to 4, so we could use the table. The probability x is less than or equal to 4 minus the probability x is less than or equal to 3, where lambda equals 6. So let's go to our Poisson table. And we need to find lambda equals 6. So we have lambda equals 6, oops, here, and 4 and 3, so 0.285 minus 0.151. I've forgotten the numbers. 0.285 minus 0.151. Which is 0.134, which is very close. So there's the two different ways you can do that. But the first case is solving this equation for lambda. And this is something you will have to do, and you need to do it correctly. So you have a quadratic. You need to handle the quadratic correctly. Don't cancel across. You will happen to get lambda equals 6 in this case if you canceled here and then this and this. You will get the correct answer, but you've left off a possible answer, and so that's not the correct way to do this problem. Okay? And that is it for this out-of-class exercises. Please take care of yourself and stay safe, because we want to see you here next time.